Good morning, student. Welcome to SYBSC Organic Chemistry Lecture Series. I am Dr. Kailas Labhade, Associate Professor, Department of Chemistry, S.VK.T College, Devdali Camp, Nasik. Student, during last lecture, we have started aromatic hydrocarbon chapter. In that, we have seen introduction to aromatic hydrocarbon. We have seen different nomenclature method, that is IUPAC nomenclature and common names for aromatic hydrocarbon. We have seen stability of benzene. We have seen aromatic character of benzene. And finally, we have seen preparation of benzene by different method, in that decarboxylation method, preparation of benzene from phenol, preparation of benzene from acetylene, and preparation of benzene from sulfonic acid. All these things we have finished during last lecture. In today's lecture, we are going to see electrophilic substitution reactions of benzene. In that, nitration reaction, we are going to see halogenation reaction, sulfonation reaction, and finally, we are going to see Friedelcraft reaction, that is Friedelcraft Alkylation reaction and Friedelcraft Acylation reaction. Learning objective of this session: at the end of this session, students should able to understand what is electrophilic substitution reaction. They should able to predict the product in nitration reaction, sulfonation reaction, and halogenation reaction. Students should understand what is Friedelcraft alkylation reaction, what are the different limitations of Friedelcraft alkylation reaction. Students should understand what is Friedelcraft acylation reaction and different reagent used for Friedelcraft acylation reactions. Now, first of all, what is electrophilic substitution reactions? In electrophilic substitution reaction, hydrogen atom of the benzene nucleus is replaced by an electrophile. In this case, benzene is shown and hydrogen atom, which is green in color, is replaced by electrophile. Hence, this reaction is called as electrophilic substitution reaction. I repeat again, in electrophilic substitution reaction, hydrogen atom of the benzene nucleus is replaced by an electrophile. We know that benzene is electron-rich species and it has pi electron. That's why benzene can act as Lewis base. It interacts with positive charge electrophile, and finally we get electrophilic substitution product. Now, in this slide, there are different examples of electrophilic substitution reaction. First example is halogenation reaction. Halogenation is carried out by using halogen like chlorine, bromine, iodine, etc. Fluorination is less common and iodination also less common. Chlorination and bromination reactions are more common in halogenation reaction. For halogenation reaction, Lewis acid catalysts like FeCl3, FeBr3, they are used. Another reaction shown here is nitration reaction. In nitration reaction, nitrating mixture is used as a reagent. Nitrating mixture is the mixture of nitric acid and sulfuric acid. In nitration, hydrogen atom is replaced by NO2 group. Another example is sulfonation. In sulfonation reaction, hydrogen atom is replaced by SO3H group. Sulfur trioxide gas can be used as a electrophile. Next reaction is Friedelcraft alkylation reaction. As we know that in Friedelcraft alkylation reaction, alkyl halide is used. Benzene react with alkyl halide in presence of Lewis acid catalyst, just like AlCl3, and there is formation of alkyl benzene as a product. Then last reaction is Friedelcraft acylation reaction. In Friedelcraft acylation, benzene react with acyl chloride in presence of AlCl3 catalyst, that is Lewis acid catalyst, and produce aromatic ketone as a product. All these reactions are the examples of electrophilic substitution reactions. Now, general mechanism of electrophilic substitution reactions. As we already discussed that benzene system is a electron rich species. Pi electrons are present in benzene. That's why these pi electrons interact with electrophile. We know that electrophile is positively charged species, or it may be electron deficient species. That's why interaction between pi electron of benzene system and positive charge of that electrophile, there is formation of pi complex. In pi complex, there is no actual bonding between carbon atom of benzene nucleus and electrophile. There is only association. In pi complex, there is no actual bonding, as we have discussed. Pi complex is not yet isolated, but its existence can be proved by charge transfer spectra. In this case, benzene react with iodine and there is formation of pi complex. When pi complex is formed, there is change in color of the reaction medium or reaction mixture. In general mechanism, next step is formation of sigma complex, or we can call it as rhenium ion or carbocation. As we know that pi electrons of the benzene interact with electrophile and there is formation of pi complex. This pi complex is slowly converted to sigma complex. In sigma complex, there is actual bonding between electrophile and the carbon atom of the benzene nucleus. This rhenium ion or carbocation can be stabilized by resonance effect. In this figure, it is shown that how that resonance effect is there. Different canonical structures are shown. Hence, that positive charge is moving over the ring, and that's why it forms the stable carbocation. Next step is aromatization of sigma complex or formation of the aromatic product. This intermediate or the carbocation is non-aromatic compound, and that's why this non-aromatic compound lose hydrogen atom. The conjugate base which is present in reaction medium that abstract the hydrogen atom, and there is formation of the product which is aromatic in nature. These are three important steps in electrophilic substitution reaction. In first case, there is generation of electrophile and the pi system, they interact with each other and there is formation of pi complex. This pi complex is slowly converted to sigma complex. Sigma complex is nothing but carbocation or rhenium ion, and that carbocation is stabilized by the resonance effect, and finally aromatization of sigma complexes take place. Conjugate base which is present in reaction medium abstract the proton and there is formation of aromatic product. Now we are going to see nitration reaction in detail. In nitration, one or more hydrogen atom of the benzene nucleus, they are replaced by NO2 group. It is electrophilic substitution reaction in which one or more hydrogen atom of the benzene nucleus are replaced by NO2 group. In nitration, NO2 plus is act as electrophile. It is generated from concentrated sulfuric acid and concentrated nitric acid. Mixture of these two acid is called as nitrating mixture. Other reagent that can be used for this nitration reaction, that is nitronium fluoroborate, that is NO2 plus BF4 minus, that can be used as a reagent for the nitration reaction. Another reagent, nitronium perchlorate, NO2 plus ClO4 minus, that can be used as a reagent for the nitration reaction. But the maximum nitration reactions are carried out by using nitrating mixture, and it is the mixture of concentrated sulfuric acid and concentrated nitric acid. Now the mechanism of nitration reaction. Nitration reaction involve different steps. That is, step first is formation of nitronium ion. Nitronium ion is the electrophile which is required for the nitration reaction, and this nitronium ion is generated from nitrating mixture. In nitrating mixture, two acids are present, that is nitric acid and sulfuric acid. one acid act as base while another acid act as acid. In this case, nitric acid act as base, it abstract that proton, and sulfuric acid act as acid, it donates proton. The intermediate which is obtained after losing water, there is formation of nitronium ion. Hence, nitronium ion is generated from nitrating mixture. It's very simple. Now, step second is attack of electrophile. As we know that NO2 plus is electron deficient species. Benzene containing pi electron, that is, it is electron rich species. Interaction of pi electron with NO2 plus take place. There is formation of pi complex. It is slowly converted to sigma complex. Hence, rhenium ion is formed. That rhenium ion is stabilized by the resonance effect, means different canonical structures are possible for this rhenium ion. The positive charge is delocalized all over the ring. That's why it is very stable or highly stable. Step third, in step third there is abstraction of proton or aromatization. Non-aromatic intermediate, that is rhenium ion, undergo aromatization and there is formation of nitrobenzene as the product. In this case, conjugate base HSO4 minus abstract that proton and there is formation of nitrobenzene as the product. This is the mechanism of nitration reaction. I repeat once again, in nitration, first step is generation of nitronium ion, and this nitronium ion is generated from the reaction between nitric acid and sulfuric acid. Second step is formation of rhenium ion, and third step is formation of aromatic compound. Now, next reaction is sulfonation reaction. Sulfonation means when there is replacement of one or more hydrogen atom of the benzene nucleus by SO3H group. That reaction is called as sulfonation reaction. Sulfonation, it is the electrophilic substitution reaction in which one or more hydrogen atoms of the benzene nucleus replaced by SO3H group. In sulfonation, sulfur trioxide is used as an electrophile. If you see the structure of sulfur trioxide, it does not have any charge, but we know that oxygen is electronegative atom, and that's why oxygen pull bonding electron pair towards itself. There are 3 oxygen atoms, that's why all electrons are pulled towards the oxygen, and that make the sulfur atom electron deficient. Now, step first is formation of electrophile. SO3, which is used as an electrophile in this reaction, is obtained from the sulfuric acid. 2 molecules of sulfuric acid, they react with each other and there is formation of SO3. Out of these 2 molecules, 1 molecule act as acid and 1 molecule act as base. This sulfur trioxide molecule is stabilized by the resonance effect, and its resonance stabilization is shown in last figure. These are the canonical structure of sulfur trioxide. Because of 3 electronegative oxygen, sulfur atom become electron deficient and it work as electrophile. Step second, attack of electrophile. Similar to nitration, pi electron interact with SO3 and there is formation of rhenium ion. It is well stabilized by resonance. And last step is abstraction of proton or aromatization. The conjugate base, that is HSO4 minus, abstract that proton and there is formation of anion of benzene sulfonic acid. In this case, anion of benzene sulfonic acid is obtained, that's why it undergo protonation to form benzene sulfonic acid. Hence, there is one more step in sulfonation reaction, that is protonation. Anion of benzene sulfonic acid undergo protonation to form benzene sulfonic acid. SO3 minus, it take proton from the solvent and there is formation of final product. These are some characteristic features of sulfonation reaction. It is completely reversible at high temperature. If temperature is high, reaction is reversible. it shows kinetic isotopic effect Kh upon Kd is equal to 2. It is called secondary isotopic effect. In presence of oleum, that is H2S2O7, carbocation undergo protonation before undergoing CH bond breaking. Oleum, that is H2S2O7, is the mixture of sulfuric acid and sulfur trioxide. Means sulfur trioxide gas is bubbled in sulfuric acid to obtain that oleum, and that oleum can be used as a for generation of electrophile. Now third reaction we are going to see here is halogenation reaction. In halogenation, one or more hydrogen atoms of the benzene nucleus, they are replaced by halogen atom. For halogenation, Lewis acid catalysts like FeCl3 or FeBr3, they are required. Generally, chlorination and bromination reactions are very common in halogenation. Fluorination is less common because fluorine react vigorously, and iodination is also less common because iodine is less reactive. Other Lewis acid catalysts like FeCl3, FeBr3, ZnCl2, they can be used as a reagent or they can be used as a catalyst for halogenation reaction. This is the mechanism. Step first is polarization. As you know that halogen molecule, both atoms are similar, means Cl2, both atoms are chlorine. That's why bonding electron pair is equally shared. Hence there is no charge on either chlorine atom. For polarization, Lewis acid catalyst is required, that chlorine interact with Lewis acid catalyst, and when polarization taking place, one chlorine become delta positive. Now that delta positive chlorine can act as an electrophile. Second step is attack of electrophile. Pi electron interact with that polarized complex and there is formation of rhenium ion. Next step is abstraction of proton or aromatization. FeCl3 minus, which is generated in reaction medium, that take that proton and finally aromatic compound is obtained, that is chlorobenzene. Benzene and deactivated benzene require assistance of Lewis acid. Benzene and deactivated benzene, we have already seen benzene require FeCl3 or FeBr3 or any other Lewis acid catalyst for completion of the reaction. Other compound just like nitrobenzene, it is deactivated benzene. Deactivated benzene means the pi electron which are present in benzene, they are withdrawn by that NO2 group. Hence pi electron are not easily available for further donation. In that case, Lewis acid is required for completion of reaction. In some compound which are activated compound, they does not react the assistance of Lewis acid. For example, aniline, anisole, acetanilide, etc. In case of aniline, NH2 group is attached to benzene nucleus, and we know that NH2 carries electron pair. There is resonance effect, electron donation of the NH2 group make that benzene nucleus more electron rich, and that's why electrons are easily available. Hence, in that case, Lewis acid catalyst is not required. Anisole is the another compound in that OCH3 group is attached to benzene nucleus. We know that oxygen carries electron pair. Delocalization of the electron pair which is present on oxygen is taking place. That's why electron density at the benzene nucleus increases and pi electrons are easily available for donation. That's why in such cases the Lewis acid catalyst is not essential or it is not required. Now next reaction which we are going to see, that is Friedelcraft alkylation reaction. During FYBSc or 11-12 you may heard about this Friedelcraft alkylation reaction. In Friedelcraft alkylation reaction, benzene react with alkyl halide in presence of Lewis acid catalyst to produce alkyl benzene as the product. Here benzene react with alkyl halide and there is formation of alkyl benzene. Generally Lewis acid like AlCl3, AlBr3, they are required for this reaction. Now mechanism of this reaction, step first is generation of electrophile. Alkyl halide is the reagent which is used for this Friedelcraft alkylation reaction. We know that chlorine or bromine, they are electronegative in nature. Lewis acid catalyst and this alkyl halide, they combine with each other, and the chlorine or bromine, which is the part of alkyl halide, get attached itself to that AlCl3. AlCl3 is converted to AlCl4 minus, and that carbocation is generated. That carbocation is nothing but the electrophile which is required for the Friedelcraft alkylation reaction. Step second is attack of electrophile, pi electron system, and that positively charged species interact with each other and there is formation of sigma complex. And in final step there is aromatization, abstraction of proton or aromatization. AlCl4 minus, which is generated in reaction medium, it abstract that proton, and finally we get alkyl benzene as a product. Rate law means rate of the reaction is proportional to concentration of aromatic compound and concentration of alkyl halide. It also depends on the concentration of Lewis acid. All these factors, that is concentration of aromatic compound, concentration of Lewis acid and concentration of alkyl halide, decide the rate of the reaction. Now in Friedelcraft alkylation reaction, some other reagent can be used instead of that alkyl halide, and that first reagent is alkene. We know that alkene containing carbon-carbon double bond. When it is treated with acid, there is formation of carbocation as shown in this reaction. This carbocation can interact with pi electron system of the benzene and there is formation of uranium ion. Once again HSO4 minus that abstract that proton and there is formation of final product which is alkyl benzene. Hence instead of alkyl halide we can use alkene as a alkylating agent. In this case acid is required for generation of that carbocation or electrophile. Other alkylating agent, that is alcohol, can be used instead of alkyl halide. Here tertiary butyl alcohol is taken. When it is treated with acid, OH group get protonated. We know that OH is very bad leaving group. When it is protonated, it is converted to OH2 positive. Now this OH2 positive is very good leaving group. It leaves the molecule and there is formation of the carbocation. Hence carbocation is formed which is required for further reaction. Once again pi electron interact with that carbocation, there is formation of uranium ion and finally aromatization is taking place and there is formation of the alkyl benzene as a final product. Now there are some limitation of Friedelcraft alkylation reaction. First limitation is polyalkylation. Friedelcraft alkylation never stop at monoalkylated state and polyalkylated products are formed. In this case benzene react with methyl chloride in presence of AlCl3 and there is formation of methyl benzene or toluene. This product is expected, but we know that methyl is electron donating group. It donates electron by plus I effect. It activates benzene ring for further reaction. That's why the methyl chloride, which is already present in reaction medium, and the methyl benzene, they react with each other and there is introduction of another methyl group at para position. Once again it react with methyl chloride in presence of AlCl3 and there is formation of polyalkylated product. Hence it is very difficult to stop reaction at monoalkylated step. Hence polyalkylation is the major limitation of Friedelcraft alkylation reaction, and we know that separation of these product is very difficult. That's why it has less commercial value. Another limitation of Friedelcraft alkylation reaction is formation of rearranged product. Electrophile formed during reaction try to convert itself into more stable carbocation. We know that in Friedelcraft alkylation reaction there is formation of carbocation as an electrophile. We know the stability of carbocation is tertiary greater than secondary greater than primary. Hence, when primary carbocation is formed, it tries to convert itself into secondary or tertiary carbocation, or when secondary carbocation is formed, it tries to convert itself into tertiary carbocation. That's why for formation of highly stable carbocation, the carbocation undergo rearrangement. That's why rearranged products are possible. In this case, benzene react with propyl bromide in presence of AlCl3. Two products are obtained. First product is normal product and second product is rearranged product. When that propyl bromide react with AlCl3, there is formation of carbocation. This carbocation is primary carbocation. That's why it try to convert itself to secondary or tertiary, and in this case secondary carbocation is obtained. That secondary carbocation again react with benzene to form another product. In this case major product is rearranged product and minor product is normal product. Now last reaction which we are going to see here, that is Friedelcraft acylation reaction. It is similar to Friedelcraft alkylation. Reagent is different. In Friedelcraft alkylation, alkyl halide is used. Here acyl halide is used. It is electrophilic substitution reaction in which acyl group is introduced in aromatic nucleus. Benzene react with acylating agent in presence of Lewis acid catalyst and produce ketone. Here CH3COCl, that is acyl chloride, is used as a reagent. AlCl3 is the Lewis acid catalyst. Benzene is the substrate molecule. Reaction take place and there is formation of ketone as a product, aromatic ketone as a product. Now mechanism, step first is formation of acylinium ion RCOCl that interact with AlCl3 and there is formation of acylinium ion RCO. This RCO carbonyl group is electron deficient, and this acylinium ion can be stabilized by resonance effect. This acylinium ion is the reagent for this Friedelcraft acylation reaction. In step second, attack of electrophile, that pi system of benzene interact with that acylinium ion and there is formation of uranium ion or sigma complex or carbocation. Now this carbocation is stabilized by resonance effect as usual, and in final step there is formation of aromatic compound. It is called as aromatization. The conjugate base which is produced here, AlCl4 minus, that abstract that proton and there is formation of aromatic ketone as a product. There are some other acylating agents used during the Friedelcraft acylation reaction. Acid anhydride can be used when water molecule is removed from two acid molecule, that is carboxylic acid molecule. Acid anhydride is obtained. Acid anhydride in presence of Lewis acid catalyst produce acylinium ion and that acylinium ion can be used for the further reaction. From carboxylic acid also we can generate that acylinium ion. RCOOH is the general formula of the carboxylic acid. OH group of that carboxylic acid undergo protonation. OH is converted to OH2 positive. OH2 positive is very good leaving group, that's why it leave the molecule and there is formation of acylinium ion and that can be used for further reaction. Hence acid anhydride or carboxylic acid that can be used as a reagent for Friedelcraft acylation reaction. Here there are some important features of Friedelcraft acylation. In Friedelcraft acylation, polyacylation does not take place as product ketone is less reactive than the reagent. We have already seen in Friedelcraft alkylation reaction, polyalkylation is taking place. But in Friedelcraft acylation reaction, polyacylation is not formed, because when ketone is formed, COR, that group is electron withdrawing group, it deactivate that benzene ring, and that's why polyacylation does not take place. In Friedelcraft acylation, rearrangement also not possible. Rearrangement products are not obtained. There are some limitations of this Friedelcraft acylation reaction. First one, acylation does not take place with highly deactivated aromatic compound. This is very important. If deactivated aromatic compounds are there, electron density which is present inside the benzene nucleus is pulled by that electron withdrawing group, and hence in that case further reaction is not easily possible. Second, Friedelcraft acylation does not take place with phenol and aromatic amines. We know that phenol containing OH group, aromatic amines that containing NH2 group, or secondary amine that containing NH group. Lewis acid catalysts interact with this group, and because of that deactivated complex is obtained. Deactivated benzene is there, and that's why further reaction is not possible. These are some limitation of Friedelcraft acylation reaction. Now, based on today's discussion, you have to solve this question and send them on my Google Classroom. First question, what is nitration? Explain nitration of benzene with mechanism. We have seen detailed definition of nitration as well as mechanism of nitration. You have to write all these things and send it to my Google Classroom. Second, give limitation of Friedelcraft alkylation reaction, that is polyalkylation and rearrangement reaction. These are two basic limitations of Friedelcraft alkylation reaction. Third is explain Friedelcraft acylation reaction in detail. Friedelcraft acylation reaction is the reaction of benzene with acyl chloride. You have to discuss all that things and send it to my Google Classroom. Now, summary of today's lecture. In today's lecture or today's session, we have seen electrophilic substitution reaction. We have seen what is the electrophilic substitution reaction, and we have seen the general mechanism of electrophilic substitution reactions. We have seen mechanism of nitration reaction in detail. We have seen mechanism and formation of product in sulfonation reaction. We have seen halogenation reaction. In that we have discussed, that is, Lewis acid catalysts are required for halogenation reaction. We have seen Friedelcraft alkylation reaction and Friedelcraft acylation reaction. We have seen various alkylating and acylating agent. We have seen the limitation of Friedelcraft alkylation reaction as well as Friedelcraft acylation reaction. Thank you.